So first, given the information up there, the first thing we want to do is find the original number of nuclei. So first, capital NO, the original number of nuclei. So we're given information about grams. So we have 0.5 grams. And now if we want to know the number of nuclei, what's the first thing I have to do? Convert from grams to what? Moles. Right. And here we want to use the molecular mass that's given to us in the form of that isotope. So here we're given information about 239. And so that's the number we want to use in our conversions. So we can convert that over, but that's going to give us moles. So how do we go from moles to molecules? Avogadro's number, 6.022 times 10 to the 23rd. This time we're going to talk about it in terms of nuclei per mole. And so that's going to give us 1.3 times 10 to the 21 nuclei. OK, so now we know the original number of nuclei. The next thing we're going to want to do is find K. And K is our rate constant for decay, or our decay constant. So what do we know about K for a first order process? We know the equation for what? For first order half-life, right. So that's 0.6931 over T a half. And in this problem, we were given the half-life. And often you'll be given the half-life, or you can look it up. And so we can put that in. So we have 0.6931 over 7.6 times 10 to the 11th seconds. And we can calculate our constant, which is 9.1 times 10 to the minus 13 per second. So now we were asked to find the original activity and the activity after 17 years. So first we'll find the original activity. And the original activity is going to be equal to our rate constant times our original number of nuclei. So we've just solved for both of these, so we can plug these in. So we had 9.1 times 10 to the minus 13 per second times the number of nuclei, 1.3 times 10 to the 21 nuclei equals 1.2 times 10 to the 9. And what are the units here? It's just like a hum. It's hard to understand. Nuclei per second, which is the same as what? That's equal to something else. Yep. So that's the same as the Becquerel or the BQ. So it's defined as nuclei per second, or number of disintegrations per second. All right, so let's do the last one. Let's see if this goes. Oops. No. Up. OK. So now, after 17 years, so now we can say that the activity at some time is equal to the original activity, e to the minus kt. And we can put in the activity that we just found, which is 1.2 times 10 to the 9 BQ times e to the minus k, which is 9.1 times 10 to the minus 13th per second times 17 years, which in seconds is 5.4 times 10 to the 8th second. So here we want to make sure that our units are going to cancel. And this is where people often run into problems. They'll plug in 17 years and then a rate constant, which was calculated in seconds, and things will not cancel appropriately. So make sure that you get your units consistent so that your seconds are going to cancel. And so this term, if we do the math out here with the number of significant figures, we find that that equals 1.2 times 10 to the 9 BQ.